Thanks for coming to class. It's pouring rain outside. See how we doing? Perfect. So, all the videos are online so far. We'll try to keep those rolling pretty steadily. Always depends on my connection. So I keep calling up my internet company to come and I get a better signal. What's wrong with this? I think we've all been through that before, but I seem to have a couple different choices on where I help them from. So hopefully we can manage everything and keep it all running together. So if we have big storms or something like that, or if you're not feeling well, definitely join us online. I'll try and keep everybody up to date. Thanks so much for being here, for keeping me company. So I like community. I like being able to see everybody and feel positive vibes. So feeling it these days. Let's come back around with this example that we have. And so this is going to be our first Bayesian example. I'm going to walk us through a couple steps. If you've taken my inference class, you've seen this example. It's the same example. And we're going to do this a couple times through a few different examples until we get the hang of it. Doing the algebra, thinking about what prior means, what posterior means. We'll keep kind of building up our examples. And before long, we'll be into a multi-dimensional example. That'll take us at least another week to get there. And so seeing things in multi-D are interesting as well, because sometimes you need to adapt your prior thoughts depending on which dimension you're living in. So, all very cool stuff. But let's start real simple with just a coin flipping model. And one of the reasons I really like this example versus the normal example that you'll find kind of the first example on Wikipedia or in your Casella inverter text or whatever text you use for inference. The normal example is also very cool. It's easy. There's a lot of agreement between classical approximate methods and the Bayesian method in the normal example. I kind of like this because there's a little bit more contrast. Also, if we think about the nature of the parameters in the data, they're not the same. So in a normal example, x's are normally distributed. And to show where the x and the mu show up, they're symmetric in that function. So you have exponential to the -1/2, x minus mu squared over sigma squared. So that's normal distribution. The x's and the mu's are symmetric. Lots of cool things happen, and there's lots of harmony in an example like that. Sometimes good to see how people think about things differently, than just kind of invoking the normal example where every branch of statistics seems to agree x bar is a really good test statistic, and the posterior distribution and the sampling distribution almost look the same in that example, except they're shifted in scale. This is completely different, however. So the nature of the data here are these two bits, a 1 and a 0. So they're indicator functions. You can think of it as flipping a coin and encoding heads as 1 and tails as 0. Or any two outcomes, a binary outcome, when there's a fixed probability P of each event. And every time I flip that abstract coin in my head, I do it without thinking about flipping in the past, my results from the past. So they're all independent of each other, they're all identically distributed. So I've written it down like this. So if you write this down for me, I know what that means. I can code that a lot of different ways. I can think of that as sampling distribution in terms of an algebraic formula or a set of conditions. And I can go back and forth in my mind real quickly. We'll go through that in a moment. I can develop the likelihood from that. So as soon as you tell me the sampling mechanism, I can write down the likelihood. In any card-carrying Bayesian, to write down likelihoods given the sampling procedure. So you write down whatever that hierarchical procedure is. In this case, there's only one step to our procedure, so it's real easy to flip a coin. But you want to be able to mimic all the stochasticity in generating the sample. And this, all the stochasticity is just developed by this coin flipping with probability P and minus P. So pretty simple. We'll keep building up the examples and understand all that stuff I just said soon. Ultimately, what the Bayesian wants to do is they want to develop posterior probability of P. So this is kind of fun to think about. So this is the probability of the probability given the x's. P is a probability. So probability over probabilities. My goodness, I've had a lot of people go, that I don't understand that at all. Anything you're ever interested in estimating, think about putting a probability distribution on it as well. So if you're Bayesian, that's exactly what you'll do. So it's not that abstract. You just think of this as a parameter that governs whether or not these are ones or zeros. This is a probability distribution over the probability parameter that generates those ones and zeros. Kind of fun to think about. Okay, our goal is to apply Bayes' theorem. So we can write down the sampling distribution right here, but we're just going to write it down and we're going to plug in our x's and think of it as a likelihood function. So mathematically they look the same, or at least, sorry, let me say that again. On paper they look the same. So algebraically it looks the same until I tell you which set of parameters or what arguments in there are variable. And so in our case, I'm thinking of this as a likelihood function, so it's the p that's variable. And my notation doesn't exactly express that. That's what I don't like about that notation. Eventually I'll just start writing down likelihood times prior. We'll do that later today as well. But this is Bayes' theorem, and you can kind of elegantly see that is Bayes' theorem. That looks exactly like Bayes' theorem. Feel good about it. Okay. So again, I'm saying that's the likelihood function, and you often hear people say that and not develop new notation for the likelihood, and they just tell you, our likelihood function looks like this sampling distribution. But what they're telling you when they say it's a likelihood is that you plug in the data and you're treating the parameter as the variable. It's not a random variable yet. It doesn't have that property. But once I pass this thing through Bayes' theorem, it gets upgraded to a random variable. That's what's really happening. Likelihood functions are not probability distributions. They can be scaled by any positive number, and they show the relative likelihood of a parameter in a ratio form. So when I take the likelihood and I divide it by another value of the likelihood, it shows us relatively how likely one point is versus another point. It's what likelihoods are doing. How do you use likelihoods? Different branches of statistics use them differently. But likelihoods, if I could go back and teach Stat 101 to everybody, we wouldn't be doing t-testing. We'd be looking at lots of likelihood functions. Let's look at likelihoods, build them up, because they kind of give you an intuition and you can think about the shape of them. We'll be looking at that in a moment. So for our example, I know what that likelihood function looks like. And I've written it down. It looks like a binomial sampling formula the way that I wrote it down, but I'm plugging in some of the xi's. I'll go through that in a moment on paper. And I'm thinking about p as the argument. And then I'm placing a prior on everything. Now, I've jumped the gun, and I haven't really motivated what I like about this prior. Now, my notation, what it's supposed to express, is that this is a distribution. I'm telling you what the distribution is, beta. That means something. If you went to a table, they would tell you what it means. I'll tell you what it means in a moment. And this has two arguments. So that function is conditional on two arguments. So until I plug alpha and beta in, the funnest part of this example is I say beta a lot of times, and it means different things. So I'll try to be a little bit clear. This right here, to me, this chunk looks like the kernel of a beta distribution. So this is the chunk that describes its shape. In a Bayesian context, these parameters are called hyperparameters. They're the parameters that you have to plug into your prior distribution to give it the prior sentiment that you want. We'll be talking about those parameters. We'll be simulating using those parameters as well and see what the posterior does. I usually like to think about, when I'm thinking about this stuff, either in a subjective context, how much data is my prior worth? So how much information am I imposing? How does it stack up against a data point, or 2 data points, or 3 data points? We'll be talking about that as well. Or, in maybe a more objective manner, I might be looking at the posterior distribution, whatever results from Bayes' theorem, and think about what impact these hyperparameters have on the posterior inference. That's what I'm really curious about. And I'll have to invoke some sort of criterion to measure things and see what kind of impact it has. Usually we like to measure against the truth. So in a purely artifactual, I should say artificial, simulation scenario, I simulate data knowing the truth, and then I can figure out how my inferences compare to the truth. When I make the comparison, I need to come up with some sort of objective function to measure how well it compares to the truth. However you do that will be subjective. But after that step, now it's all objective. So lots of ways to think about this. I want to point out, it's not completely arbitrary that I picked this shape of prior distribution. It has to do with the shape of the likelihood function. So let me just say this. If I have a prior distribution and it lives in some family of distributions, so this is a beta family of distributions, and the posterior distribution also lives in that same family of distributions. So if it so happens that this posterior is also beta, what we would say is that that prior is conjugate. I'll write that down in a moment. So those of you that are swift with your algebra have realized that this is the conjugate prior. Now that's on its own, that's just something that's convenient for me. If I know the form of the prior, I know the form of the posterior, and ultimately what you're doing is you're just updating the parameters in that distribution when you see data. So that's kind of the sequential updating sort of mindset on everything. Bayesian analyses do that. Okay, so let's do this on paper. So I'm going to switch over. I'm going to try to say everything again and also do some writing as we go. So I've done the easy part. I wrote down, this is going to be the Beta-Binomial Example. It's named Beta-Binomial for hopefully obvious reasons. Could I have called it Beta-Bernoulli? I could have. That's fine. So we'll talk about that in a moment. But the xi's are Bernoulli. That just means they're coin flips with a probability of heads, or 1 being probability P. The probability of the other side is the complementary probability, i.e. 1 minus. Okay. Just for clarity, xi's 1 and 0. That's it. So when you describe a sampling distribution or something like that, you should tell us the range of the parameters. And I haven't done a very good job there. I've told you this is a probability, but I should probably say P itself is an element of 0 to 1. So this is a continuum. So this is what I was trying to allude to. What I really like about this problem is the xi's are discrete and the parameter space is continuous. It's also constrained between 0 and 1. So they're totally different things. The normal example, when you flip everything, it's continuous. Everything's normal in the example, and maybe that causes a little bit of confusion because it's one of the only examples. Special things with normal distributions. Okay. So that's our setup. So I've written this down. Ultimately, I've also stated this exact same thing. So this is a different way of saying everything. Xi's are distributed according to this sampling function. X is a dummy argument. P is going to be fixed in set. So if I'm going to sample this Xi, I need to plug in a P. X is just denoting the space where everything lives. If you look at real mathematical stuff, they'll tell you what the random variable is, the instance of the random variable. I'm going to do what every other statistician does and just write X. And if you understand the minutia difference, that's good. Well, oh yeah, absolutely. Yeah. 1 minus. So that's all in the exponent there. One minus xi. So really that's just acting as an indicator, and it's either turning on p or turning on 1 minus p, the way it's encoded. So it's the same thing. You'll get good at this. As you start to see a lot of examples, you want to turn things on and off in the equation, you're either going to use an indicator in the exponent or right out in front, depending on if it's an additive thing or a multiplicative thing. So if it's in the exponent, use that for turning things on and off in a multiplication sense. You want to turn things on and off in an addition sense, you put the indicator right in front of the thing, multiply it. Go through lots of examples where you'll see this. So I think I wrote it like this first. I like writing it like this most of all because it's ready for me to operate with on a computer. It's an algebraic expression. And so I personally like this, but it's really easy to represent this way. I'll point out that x bar is a very important quantity in all of this. I'll say a little bit about this in a moment. But x bar does turn out to be a good estimator for p. We'll see that. That's stuff you probably already know. Depending on which statistics classes you've had, most paradigms of thought think that x bar is a really important estimator for p. Okay, I'll just point out n times x bar right here, that's the sum of the ones or zeros, which represent the number of successes. So that's what that is. That's binomially distributed. And that distribution looks like this. P to the sum of the xi's. 1 minus p to the n minus sum of the xi's. And you can derive one from the other. And if you haven't done this in a while, go ahead and do it. Show that transformation of variables with sum. I can think about it in a lot of different ways. But you can use your convolution formulas. You can do a direct transformation. You can do it with just 2 random variables and induct. So all stuff that I think you can do. This has a normalizing constant out in front. This is n choose the number of successes. So let me write that down. So this is a normalizing constant. We're going to talk about this word constant later. Sometimes you can get confused on what's actually constant about it and why is it called a constant. It might not actually always be a constant with respect to the Bayesian analysis. In this case, it doesn't have anything to do with p. So it's constant with respect to p. But what this does is it counts the number of rearrangements of these vectors. 1, 0, 1, another 0 and 1 there. So whatever the data looks like right here, it's just counting the number of rearrangements of that I can distinguish from each other. So if I interchange 2 1s, I can't tell the difference. So if I interchange a 0 and a 1, however, in position, I can tell the difference. This is just a combinatorics for counting that. And hopefully you know what that is. Okay, so it doesn't matter which formula I actually use. We'll find out in a moment. We can just switch gears. We know what the sampling distribution is, but what we really need to do is write down the likelihood. Kind of have done that already. So I'm going to write it down a whole bunch of different ways. I want to remind you about this proportionality constant, or proportionality sign. So I can multiply whatever this formula is by any positive number, and it's still valid. So you can try to multiply it by like a Googleplex or something like that, and bring it into your MCMC code and watch things go wildly wrong. So if you multiply by too big or too small of a number on a computer. But in mathematical land, without respect to any truncation or rounding of numbers, it doesn't matter. In practical senses, usually care when I multiply. But we'll talk about that later. Okay, so I could go back to this formula, the sampling distribution for my xi's. I could product that together, and I can think of that as the likelihood function. So I could just write down product. I goes from 1 to n, p to the xi, 1 minus p to the 1 minus xi, and that's my likelihood function. And what I'm trying to explain in this notation is p is the argument. That's the way I do it. Other people do it differently. So they probably want to preserve the way Bayes' theorem looks. I like to preserve what the bar means. So it doesn't really matter how you think about it. It just matters in terms of how you convey the information to somebody else. Okay, this, I could write this down like this. I could also simplify it. So this is going to be equal to p to the sum of the xi's times 1 minus p to the n minus sum of the xi's. Just when I brought it through, the exponents add. That's all it's saying. So these xi's are either 1s or 0s. So this count, this sum up here, is counting the number of successes. And this is counting the number of failures. So let me just rewrite that. Say that this is the number of 1s. Often I call those successes. Or 0. Always a failure. Number of failures. So that's what that is. I could have done this a little bit differently. I could have written down using my binomial expression. So if I like working with the binomial up front, I know that sum of the xi's is a sufficient statistic. What that really means is that it's the sum of the xi's that are important about this equation. I don't really care where the 1s and 0s landed. The only thing that is informative about this likelihood function is the sum of the xi's. The data is only informative through that number. It doesn't matter where they were located, because it's an IID example. So the arrangement doesn't matter to us. So I could have written down, my likelihood function was this. Could have just dropped down my binomial formula. And I'm going to stop writing the indices. They all go from 1 to n. Inside, and I did the same thing again. N minus that in the exponent. You'll notice that these two things are proportional to each other. And it always will be. So if you're using the sufficient statistic, if you know about that, it's going to be proportional to the likelihood function. I should say, if you use the sufficient statistic to derive your likelihood function, you're going to get the same likelihood function that you would get if you just went through the actual individual data elements. Now, of course, I would never code that up on a computer right there. That would scare me, because I got this big product. I probably need to keep evaluating it every time I evaluate everything. Probably unstable if n got big, and if these p's happen to be small or big, this thing is going to be numerically very unstable on a computer. This will do better. It has less computation time if I store the sum of the xi's, but this is also numerically unstable probably on a computer as well. Saying that my example is simple enough that I did encode everything this way, but we'll be talking about that later on when we get to MCMC, that we probably want to work with log likelihoods. It takes small numbers and makes them bigger, and it makes big numbers and it makes them smaller. Usually that's enough to save us a lot of headaches. Talk about that later. They have one-to-one relationships to each other. So when I do write things down on paper, I'm always thinking about, would I actually code that up like that? So that's something I'm always looking at. these two functions right here are proportional to each other, and that's how we're going to use everything in our equations. So this is our likelihood. I don't care about that. I can multiply by an additional like 10,000 right here. Still my likelihood function. Or this is my likelihood. So I would probably work with this one right here. But wherever I use this thing in my formula, I always have to be consistent with my form of likelihood. So I can't take the likelihood in the numerator and use one arbitrary constant and use a different form of the likelihood in the denominator with a different constant. You need to be consistent. I think that's pretty obvious. Okay, priors. So this is our first foray into prior distributions. And I think I'm just going to tell you the definition of conjugate priors. What I'm going to keep doing is I'm going to tell you good things about priors and bad things about priors as we go. And it turns out for a lot of applications, especially in things like the exponential family where we'll be doing a lot of our analyses, distributions you're familiar with, conjugate priors are some limit of a conjugate prior. Is going to have optimality criterions that you might like. So it turns out quite regularly you use conjugate priors or limits of conjugate priors. And so depending on what your objective function is going to be. Right now, the way I'm motivating this is it's purely for convenience. It makes our life easy. Algebraically, we can sequentially update. Later on, I'll fill in the gaps and say, we use them all the time. Some of them have really good problems. Which one do you want to pick? Well, get into that. I.e., how do you set the hyperparameters? Clearly matters. Okay, prior distribution. So let's just start with a definition. Conjugate prior. I want to point out that if you're into linear algebra, which certainly everybody in this class is into, complex analysis, all kinds of people use this word conjugate, and we use it totally different from each other. So this is a new way, and it doesn't have much to do with what you did in complex analysis a long time ago. Okay, so this is just a word that's being recycled, and there's other words like that people just kind of throw around. Sometimes they have more relationship to each other, like invariance, but what it's invariant to, you have to be very careful about. And so, anytime I see these words, I usually ask, what does it mean in this case? So I'm going to tell you what it means with respect to prior distributions. If, we'll say, the prior lives in a family. I'll give you some examples, e.g. beta, normal, croissant, etc. So what I don't mean is the exponential family. And I say that sometimes. So exponential families are really big families that encapsulate a lot of distributions. So I don't mean this big family of families. Just a quick question since we're in a stats class. Why do you like exponential families so much?
Because it takes what likelihood of them and it crunches exponential to a sum or something easy to calculate.
Yeah, I mean, what I think about, that's all true. What I like about them the most is that the sufficient statistics are usually something that I can compress. So computationally, it always has an advantage if I know I'm working in that. I.e., the likelihoods aren't big products and things. That's what I like about them. Saying that, they have nice canonical forms that we can relate distributions to each other to. So there's practical reasons why you might like them, and then there's theoretical reasons that you might like them. So I happen to know if I'm doing a regression of this type, the canonical link is always going to show up here in the formula. I know what it is, and that will work. So can I use something else? You could. So sometimes theoretical, and sometimes it has some real practical stuff. But I mean a specific distribution. So normal distribution, Poisson distribution. We're going to lock down that functional form, not families over families. So if a prior distribution lives in a family, and I'm going to call this F, my family. That doesn't say family. Family. So I'm going to call that family F, and the posterior distribution give these some names. I'm going to call this pi p. I use pi a lot. My functions, when I'm doing Bayesian stuff, I'm not sure why. So if my prior pi p lives in F, and the posterior pi p, given the data, usually write that as cap x or something like that, also lives in F. It's a different distribution in the same family. That means the parameters governing that distribution are different. That's all that's different. But the mathematically functional form that controls the shape is the same. So also lives in F, then pi p is called the conjugate prior. So usually people say, what's the trick? What's the secret to figuring out what the conjugate prior is? And I always give the same trick. You have to think about it. You have to recognize it. So if you don't know what the distributions are and what they look like, it's going to be impossible for you to just recognize them out of nowhere. So and be familiar with what that distribution is. But what you really do is you look at the likelihood function. And you think about what can I multiply by and slides through and has the same functional form. Algebra changes in a lot of different equations, so you have to do a quick manipulation in your head. But let's look at the example that we're working on. So back to our example. We have our likelihood. Cap x proportional to p sum of the xi's 1 minus p n minus sum of the xi's. What am I going to multiply by? I always do the same thing. I take whatever is multiplied there, throw it away, and I replace it with 1. So, and then I never even write it down. So on a computer, that's good. I don't have to multiply by it. Saves me time. Also helps me with rounding. There's never going to be a number that you can multiply a small number and bring it up a little bit, because once you've already written down that small number and you do the algebra on the computer, it can't fix it for you. So I just multiply by 1 right here. That's the shape. We'll be looking at this shape in a moment in our prior, the conjugate prior. Write down likelihood. And then the prior. And there's only one here. There's only one conjugate prior. Conjugate priors are unique. Likelihood functions are unique. So it's the likelihood function. I mean, you can multiply something so without worrying about a multiplication constant, invariant to that, they're unique. So the conjugate prior is going to look like this. And I'm just going to mentally think about what can I multiply this equation by, what mathematical function, so that I have something of the same parametric form after I multiply it. And I have to know how exponents work. how all that data comes into play, and what happens with the p's here. I can do this pretty much in my head because I know the answer to it. But if I look at the conjugate prior, it's the beta. So what I can convince myself of real quickly, if I multiply this function into this, I'm going to have p raised to some power and 1 minus p raised to some power that looks like a beta again. I'll do that multiplication in a second. I just want to walk you through some terminology real quickly. This right here is the kernel of the beta distribution. You can say density if you want here. That's probably what I should say, because this is a density. So sorry, that's my one thing I can never get over, is swapping density distribution. I always just say distribution as a default. And mark me off on my midterm if you'd like. I won't mark you off though. This right here is called a beta function. I'll ask you about that in a second. And these right here are hyperparameters. Hyperparameters are parameters that live inside of your prior distribution. The parameters that you choose to either invoke information you know about subjectively, or they're knobs that you turn to get the right objective criteria. There's a lot of betas running around. I have beta denoting one of my hyperparameters. I have a beta kernel, and then I have a beta function. And the beta function is just this integral. P to the alpha minus 1, 1 minus p to the beta minus 1, from 0 to 1. pt. This is equal to this function inverted. It's the inverse of that function. It's the normalizing constant. So what do you do to figure out the normalizing constant? You add everything up, and then you divide by it. So there's no closed form solution to this. It can be written in terms of gamma functions. Sometimes people will say that to me. Looks like this. Gamma alpha plus beta. Gammas are also a function that you cannot express without an integration, unless alpha and beta are integers. And then it relates to a factorial form. You can look all that up on Wikipedia. I think most of you know it. Saying that, I don't really think too much about this function too often because I don't use it. It ends up canceling out in most of my analyses, and I don't need to think too hard on it. It's the thing that normalizes the beta kernel so that it's a distribution that adds up to have area 1 under the curve. That's just all some terminology for this example. Okay, let's just look at the posterior now. Once I have my prior and my likelihood, I'm done. That's phase. So prior likelihood. I don't think I could go to a scientist and say, well, here's your likelihood function and here's your prior. There's your analysis, please pay me. For one, nobody ever pays me. And for two, I don't do any consulting these days. So I'm just tired of it. I'd rather have my weekends. So for scientists and engineers at the university, I do a lot of analyses for them. I don't go up to them and say, here's the likelihood and here's the prior. You figure it out. So it's true, your analysis is kind of done and set. Oftentimes we have to remodel everything. So coming up with likelihoods in the first place has to do with what you actually think is generating the data. So usually it's an iterative process. But in spirit, if I knew the sampling distribution I had whatever my prior beliefs were, my Bayesian analysis is just turning the crank. It's already been set up. From a purely qualitative perspective and an applied statistician perspective, nobody ever hands you anything. So you just get a bunch of crazy data and you need to do something with it. So this is a little bit of a fiction where I get to say I know where the data came from. But the posterior distribution is just going to look like this. In our case, the sufficient statistic is sum of the xi's. That's how the data is coming in. If you don't know that term, that's okay. I'm not going to test you on it. But this is going to be proportional to the likelihood times the probability. A lot of people will not write down their hyperparameters when they express this. So they'll suppress that from the notation. I like to write it in quite often. I usually like to talk about how I pick those parameters, but I think a lot of people suppress the notation because they don't want you to ask too much about it. Sometimes they have some objective method that picked them for it, so it was never an argument in the first place. But I'm going to keep writing that down like that. So this is just equal to p sum of the xi's, 1 minus p, n minus sum of the xi's, times p to the alpha minus 1, 1 minus p to the beta minus 1. So it's just a product of these things. So I'll just write times right here, put a times sign right here. And this, at the end of the day, is p to the sum of the xi's plus alpha minus 1. 1 minus p, the n minus sum of the xi's, plus beta minus 1. So that's the thing that you're thinking about up front, is when you pick the conjugate prior, you're thinking about a prior that comes out in the same form. What does this look like? It looks like p to the sum exponent times 1 minus p to some exponent. I know what distribution that is. P lives between 0 and 1 still. Never change that. That's a beta distribution. That's a beta density. That's what it is. There's no other way you can do this. You can probably convince yourself just in your mind that if you multiply by anything else that didn't have that beta form, it would not come out as whatever that form is that you're trying to push through and slide through the likelihood. There's only one way to do it. So know your distributions is kind of step 1 in this class. If you know them, everything's really easy. So I know that this is a beta, and I know what the functions are, or what the arguments are. They show up right here. So this is a beta with these updated arguments. So if I go back to my original notation on what a beta was, I just had alpha and beta in there. These are the updated parameters. So conjugate analyses are nice because you're just updating the parameters in the distribution. That's all you're doing. And you can imagine the poor 1960s Bayesian trying to convince everybody what they're doing is good and it's easy and it works well. They don't have computers, so they don't have many choices, so they need something that they can kind of work with easily. Again, I'm going to promise you later on, it's a little bit better than it sounds. It sounds like it's just there for our convenience, but it turns out if I were to operate with ones and zeros, I believed everything was Bernoulli, it was this IID process, I'd be going off and running with some beta distribution as my conjugate prior. First thing you want to ask is what distributions do you know that live between 0 and 1? Are continuous. If you pick anything else not continuous between 0 and 1, it doesn't even make sense. So it has to cover the right area. Okay, I want to show you a simulation, we'll come back to this next time, of what all this looks like. So we've got our formula. I won't go to my scientist and say, you know what? I've done your analysis. Here it is. That's it. It's what I think. It's not a very good way of looking at things. So let me first tell you what I would show them. If I were working on a problem simple enough like this, I'd show them what likelihoods look like, what the priors look like, and I'd try to get them to think about what it all means. Before I give them, here's my conclusion. So, and I think this is a good thing for statisticians to do. I wrote a piece of code that implements all this. I'll walk you through this code. Right when we come back next time, I'd rather just leave you with an example in the last 3 minutes. But I wrote a piece of code that takes in some numbers. So this is my sequential binomial pure Bayes. I have other versions of this code that I show frequentists and classicists and show them how it compares to that sort of analysis. We can look at that later. But it takes in a few arguments. It takes in true P. So I have to simulate the data. So it's going to take that in. And all it's going to do with true P is it's going to simulate the data and it's going to plot where true P is. So I'll never use it in my inference. I don't get to know what the truth is. So that's how all simulations will be performed. I take in alpha and beta. Those are my hyperparameters from my prior distribution. So I can play around with that. And I can evolve my posterior as a function of the number of times I flip the coin. So I'll show you the posterior update. And I think that this is pretty illuminating. So, I don't know, how do you guys want to pick alpha and beta? Any choices? Here's what I'm going to do. Since we're low on time, I'm going to pick up to be 1 and 1. This is not what I normally do. But a lot of people like that. What a beta 1 is a uniform distribution. Perfectly flat. Think about the exponents. They have 1 subtracted off of them. So I have p to the 0, 1 minus p to the 0. That's proportional to 1. That's a uniform distribution of lives between 0 and 1. So maybe that's the non-informative prior. I actually use something that's even less informative in some sense, and I have to tell you what that means. But let's just go with this. So there's my prior with a dashed line, and my truth is at 0.7. Okay, so that's how I'm walking in before I see any data. So maybe you like that prior because it equally weights everything. To try to convince you about some other priors later on. There's my likelihood function after 1 coin flip. I showed you the draw as 1. So my likelihood function is p. And that's a straight line. Scaled a little bit funny. I've normalized my likelihood so that they'll plot well against everything else. I'm going to flip the coin one more time. I got a 0. Look at that likelihood. What it just did on both endpoints is it ended up saying there's 0 likelihood of it being a 0 or a 1. I just saw both instances. P can't be 1 and it can't be 0. Where does it maybe think it is? It's somewhere around here. We get some more draws and watch this thing evolve. So I keep getting some 0s, now I'm getting some more 1s. And we see that this thing has moved. It's changed shape in a lot of ways. I want to come back next time and dwell on this a little bit more. I know the class is really slow for people that have taken my inference class, so this is just a friendly reminder of things you know, but we're going to extend all this to other distributions as well. What I want you to see is how that posterior just adapted. It was straight line, then it was heavily skewed, and it's starting to look more and more symmetric as we start to go through things. I want to talk about all of those points. But really, this is what I think the Bayesian analysis is this curve that we're drawing. And that curve should be able to adapt and be able to hone in on the truth. That's the goal of all of our analysis. All right, that's it for now, you guys. Thank you very much. I'm going to have office hours for a little while. You guys feel like going over to my office in Hutchinson, that's okay. I can hang out in the foyer for a couple minutes since there's not too many of us. But let's just remember to kind of distance as well. So if you guys don't want to walk back,